Hello, in this lecture we'll be studying about buck boost converter. It can perform both buck and boost operation. That is, it can both step up the voltage, that is increase the voltage more than the input voltage, and step down the voltage, that is decrease the output voltage less than the input voltage. Now let us look at buck boost converter. Buck boost converter has two characteristics. It can perform as a boost and as a buck depending on certain criteria, actually depending on duty cycle. That is, at some cases it can make V output greater than V input. At some cases it can make V output less than V input. So it can perform both buck operation and boost operation. This is the circuit. We have a switch, an inductor, a diode. The orientation of the diode is noteworthy, and a lumped resistance and capacitance as acting as a load. And we'll be considering on state and off state operations for our mathematical analysis. During on state, current flows in this direction and no current can flow through here since the diode will be reverse biased, and as a result, if we denote this as Vi and this as VL, using KVL we get minus Vi plus VL is equal to 0, or we get VL is equal to Vi. We give this equation number 1. When the switch is off, we can see no current can flow through it because this is open circuited. As a result, current will have to flow in this direction. Why this direction? When the switch was on, the inductor was being charged and current was coming in this direction. So the current has to leave through this direction when it gets discharged. And again, current cannot go in this direction since there is a diode involved and the direction of the diode would be opposite. As a result, the current has to flow in this direction. So we apply KVL in this direction. Similarly, we denote VL. V output we get by applying KVL, VL minus V output is equal to 0, or VL is equal to V output. We put it equation number 2. Now over one complete cycle, we know 0 to T, VL dt is equal to 0, or 0 to T on. When the switch is on, we get VL is equal to Vi plus integration of T on to T. When the switch is off, we get VL is equal to V naught. We get this 2 from equation 1 and 2. So summation of these two will be 0. From there we can get Vi T on minus T minus 0 is equal to V naught, plus V naught T minus T on is equal to 0. From there we can write Vi T on plus V naught T minus V naught T on is equal to 0. From this we get Vi T on divided Vi T on is equal to V naught T on minus T. Now Vi T on we have already seen is equal to V naught T on minus T. So we get Vi into T on divided by T on minus T. T on minus T is equal to V naught or V output. So we divide the top and bottom by T on. We get Vi T on by T on divided by T on by T on minus T by T on. V output, or we get V output is equal to 1 minus 1 by D. Since T on by T is equal to D, T by T on will be 1 by D is equal to into Vi, or we can modify it as V output is equal to T by T minus 1 V input. So this is the voltage relationship of buck boost converter. Now we note that we have said that it can work as both buck and boost. If D is below 0.5, let us suppose is equal to 0.4, we can take any arbitrary value. We get V output is equal to 0.4 divided by 0.4 minus 1 V input, that is 0.4 by minus 0.6 V input, or V output is equal to minus 2 by 3 V input. Now we see, firstly 2 by 3 is less than 1, so V output is less than V input, so this is acting as a buck converter. Again, it is to be noted that there is a minus sign. In case of buck boost converter, the output is always opposite of input, that is the polarity of output is always opposite to input. We can say again, if t is greater than 0.5, we get V output is equal to, say it's 0.6 for our calculation, 0.6. So we get output is equal to 0.6 divided by 0.6 minus 1 into Vi, that is 0.6 divided by minus 0.4 Vi equal to minus 3 by 2 Vi. Again, we note that we have that minus sign because this is the characteristics of buck boost converter, and again 3 by 2 is equal to 1.5 greater than 1. As a result, V output will be greater than V input. So as a result, we can see when the duty cycle is above 0.5, we get boost operation, and when the duty cycle is below 0.5, we get buck operation. Now the current relations are almost similar. From equation 1, when the switch is on, we have found VL is equal to VI, or IL is equal to VI by L T. So as a result, it will have a positive slope, as we can see here in the on state. In the off state, we have found VL is equal to V output, IL is equal to V output by L into T in the off state. But we note that V output is opposite polarity of V input, that is, if V input is positive, V output is negative. So this has a negative slope. As a result, current decreases. So again, the condition of continuous conduction mode has to be considered while designing. Now if we want to measure the current input output current relations, we can see when in the on state, I input is equal to IL. In the off state, I input is equal to 0. Again, in the on state, I output is equal to 0. In the off state, I output is equal to IL. So we can note that I input is IL when the switch is on, that is, I input will be T on by T IL, that is T into IL. Similarly, I output is equal to IL when the switch is off. So we can write T minus T on by T, that is IL 1 minus T. So from this we get I output by I input is equal to IL 1 minus T divided by IL D. From where we get 1 minus D divided by D. So I output is equal to 1 minus D by D I input. Again we can see, if we that if D is greater than 0.5, suppose 0.6, then what happened is 1 minus 0.6 by 0.6 into I in is equal to I out, that is minus 0.4 by 0.6 I in is equal to I out. That is, this is greater than 1. As a result, I input is greater I output is greater than I input. So if I output, sorry, this is smaller than 1, so I output is smaller than I input, so this follows boost operation. If D is less than 0.5, suppose D is equal to 0.4, 1 minus 0.4 by 0.6, I in is equal to I out, or 1 minus 0.4, sorry, so 0.6 by 0.4, I in is equal to I out. As a result, we can see that output current here will be greater than input current. So when D is less than 0.5, it follows boost less than 0.5, it follows buck operation. So we get, in case of buck boost, if D is above, duty cycle is above 0.5, it acts as a boost. If duty cycle is below 0.5, it acts as buck. That's all for this lecture. We'll be learning about the other DC-DC converter in our next lectures. Thank you.